Hey everybody, Mr. Murphy here, and I'm going to take a quick look at Chapter 2.5 and an introduction of some concepts of energy. So, throughout biology, we see tons of chemical reactions happening. We see the buildup and breakdown of molecules, we see the creation of new molecules, all sorts of things. We have reactants, that's the things going into a reaction. We have the products, the things coming out. When we talk about metabolism is kind of a tricky word. It's really just like all of the chemical reactions happening inside of a biological system. So when we talk about like, oh, this person has high metabolism or I have low metabolism, we're just sort of like vaguely talking about in general just like how much activity is going on inside of the body. And that relates directly to energy usage and therefore can be related to like weight gain and weight loss and things like that. In general, I think people probably too casually use that term to sort of describe those things, but there is an underlying basis for it. When we talk about energy, this is going to kind of feel a little bit like physics class. It's all potential energy and kinetic energy, but not like gravitational potential energy, but it's a different kind of potential energy stored in chemical bonds. In terms of kinetic energy, it is exactly the same as physics, a whole 1/2 mv squared kind of a thing. We don't need that equation for biology. That equation makes a little bit less sense, but if you've taken chemistry, which you probably have, you've seen how kinetic energy plays into the movement of molecules and the energy they carry as that is occurring. So energy is constantly being converted from one form to the other, and there's some rules of thermodynamics that kind of play into this. You're not going to get quizzed on like the laws of thermodynamics or anything, but it's good to just understand some general basic facts about how energy works inside of molecules. We have two main types of reactions that are occurring inside of biological molecules. We have anabolic reactions, which are ones that are linking smaller molecules into larger ones, essentially need energy to be input because they're storing energy in these larger molecules. And then we have catabolic reactions, which is the breakdown of the big stuff into smaller pieces, and this is where energy is being released. So here some other terms to describe this is endergonic and exergonic. Endergonic reactions are one where the energy is being stored. And so here you see like a ball being rolled up this hill. That's very similar to the idea of you have reactants and you're building those up into larger products that are storing energy within their bonds. That requires energy to be input. So endergonic reactions require energy going in. Exergonic is the exact opposite. You're taking something larger and you're breaking it down, releasing the energy within those bonds as you break it down into smaller and smaller pieces. Thermodynamics fits in that we have to understand some basic things about energy. First off, energy is never created or destroyed. So here is a representation of this. Whatever energy you have in a system before a reaction is the same energy that you have after the reaction. The important thing to understand, though, is in the second law of thermodynamics, we talk about the usability of this energy. So even though the energy before and after is the same, that energy has changed forms and will continuously become less and less usable over time. And so here you can see a representation that shows you, yeah, it's the same energy, but we've broken this down and released some component of energy that's not going to be immediately usable, and that most often falls in the lap of the idea of heat. That heat is produced, and heat is just kinetic energy of molecules bouncing off of each other, and that can be helpful in the facilitation of reactions, but not all of that can be captured because on a molecular level you got stuff bouncing all over the place. You just can't capture every little ounce of that energy. And so what that means is here's a representation sort of showing you that if you had a closed system with just a bunch of reactions happening, yes, the total energy of that system is the same throughout, but will become increasingly unusable until you've used up every bit of usable energy, and now you just have basically heat that has been generated, kinetic energy that's been given to things. So we refer to this as entropy, that increasing chaos and unusable energy that's in a system. So chemical reactions increase entropy, which means that it's becoming a little less ordered and or a little bit more disordered and random than the reactants were. So think like a glucose molecule contains energy, right? And a mitochondria is going to subsequently break that down until it's made CO2 and water, and it has also generated some ATP. but in that process, it's also generated a bunch of heat. So not every bit of energy that was in that glucose molecule is going to actually be usable by the cell or the organism. It's a little more complicated than that because for us being warm-blooded organisms, we do benefit from the general heat that is generated by that process. But again, we're constantly losing heat to our environment, so there is this constant energy loss. So, to summarize, with metabolism, it in general is creating more disorder as energy is lost, and all of these reactions inside of us are constantly doing that. However, we are able to utilize those breakdowns in a variety of ways in order to effectively allow for life to continue. In the end of this chapter, it returns to the opening question of, why do we look for water as we are exploring for life on the moon or Mars or exoplanets or things like that. And these macromolecules and water are demonstrated to be necessary components for the creation of the variety of molecules that we see as being essential to all of life on our planet. And in the 1950s, there was an experiment conducted by two individuals, Miller and Urey, which demonstrated this quite effectively, and subsequently demonstrated how easily chemistry could be responsible for all of the necessary components that make up biological life in a relatively simple way. We'll return to this when we get to our later units on evolution and we look at first life theories. But essentially what they did was they took all of the sort of chemical markers, chemical components that we know from geology and a variety of other ways that were the makeup of the early atmosphere, and they stuck them in a container and they zapped them with electricity, mimicking things like lightning. They heated it up. The Earth was a very warm place in the early days of life on this planet. There was a lot of energy input. And when they let this run for a period of time, they demonstrated the ability to make essentially all of the amino acids that we find inside of organisms and countless other macromolecules as well. So there's a lot of cool stuff that really has demonstrated how significant chemistry is as a force within biology, not just in everyday surviving, but also in terms of understanding where did life come from to begin with. So that's cool stuff that we will dig into much more deeply later on, but it's a nice way to sort of close out this chapter on biochemistry. If you have questions on anything of Chapter 2, let me know. Chapter 3 continues with proteins and enzymes and all that good stuff.